Sure, sir.
Yeah, let's keep going. Yeah, good. All right, so that's the spirit. So next we are going to discuss the Clausius inequality and reversible, irreversible processes. So Clausius says Clausius's inequality. So far we've been discussing reversible engines or reversible systems. Uh, what is it when we have irreversible engines? That means we have some friction going on, and that means that some of the heat or some of the heat is radiated into the environment, and our engines are not as efficient as we would like them to be. So, for example, the work done by a heat engine, which is irreversible, say suppose it absorbs heat H, QH prime. Again, I'm going back to the old notation where everything is positive. So the efficiency here is not going to be um, as much as a Carnot engine. So we are talking about a heat engine which is working between temperature TH and TC. So this is a irreversible heat engine. Okay. So it's not as efficient as a reversible heat engine. And suppose that we have a Carnot engine which is acting between the same temperatures, which is working between the same temperatures, and it takes in work, and then it's converting that into it's absorbing heat and dumping heat, and it's converting into work, right? So now what we can show is that given these two engines, the quantity of interest, which is the heat over the temperature, for the irreversible engine. So for the irreversible engine, this thing can be written as QH minus by TH, QC by TC, minus QH prime minus QH over 1 over TH minus 1 over TC. Okay, so this is not obvious that you can do that. Okay, so to be able to do that, you have to use the fact that the Carnot engine, that for the Carnot engine we have QH over QC is TH over TC. Okay, so this is just like, these are a few lines of algebra. You just start from the right hand side and you can show it's equal to the left hand side. Okay, and also for the Carnot engine, using the since the efficiency of the Carnot engine is greater than the efficiency of the other heat engine, from that you can show that Q prime is greater than QH. Okay, and for the Carnot engine, for any heat engine, the TC is greater than TH is greater than TC. So these together mean that the left-hand side of this equation, is actually negative. Okay, so Q prime of H, T of H minus Q prime of C, T of C is less than or equal to 0. Okay, so this is a short exercise that I'm leaving it for you. Okay, is that all right? In fact, I think I did the, I in the last lecture notes. Okay, Farhan, you raised hand. Do you have a question?
No, sir.
Okay.
Accidentally.
Oh, no worries. Yeah. Okay, so so by the same argument that we did before, you can show that this means that if you go for a for a for a for a for for an irreversible engine, that dq by dt is less than or equal to 0. Okay, and so this is for irreversible engines. Okay, so not reversible. We are not defining entropy here, right? So for irreversible engines, this is less than or equal to 0. Actually, for any engines, because what will happen is that if the engine is reversible, then it'll saturate the inequality. Right. So this is Clausius's inequality. Now let's use Clausius's inequality for irreversible engines and the definition of entropy together. So suppose that we have two states, A and B, and A is connected to B through some path 1, and then we go loop back through path 2. Now we assume that path 1 is an irreversible path, meaning that if we travel around path 1, we lose some of the heat. We generate a friction, and I will come and I will give you some examples, some real life examples, as real life as it can get in theoretical physics, examples of an irreversible path in the next lecture. But we are saying that the path 2 is a reversible path. Okay. So then, according to Clausius, that dq over t over this closed path is 0. So it's less than or equal to 0. Now we can divide it into two paths, right? We can have path 1, which goes from A to B. So we have dq over t, and then path 2, which goes from is path 2, which goes from B to A, but path 2 is a reversible path. Okay, and therefore we can write this as dq along path 1 is equal to the integral over path 2, but now going from A to B, because we took it to the other side. So there was a minus sign, but we changed the order of the integration. And we can do that because the second path is reversible. And because it's reversible, we can assign to the end of this path some entropy. So we can write, sorry, are people sleeping? Because you should have told me that I made
I was
use
gonna
of.
say that.
Okay, good. Awesome. Yeah. All right, good. So this is going to be less than or equal to S of B minus S of A. Okay. So now suppose that path 1 is irreversible, but it's also adiabatic, meaning that it's isolated, right? And then if it's adiabatic, that means that along the path 1, we can have dq equals to 0. Then we see that S of B is greater than or equal to S of A. Okay. So what does this mean? This means that the entropy of an isolated irreversible system or process, let's call process because otherwise it's a bit confusing. Never decreases, okay? So you have some, irreversible system, but you isolate it from the rest of the universe, or you can think of the irreversible system as the universe. Then, as time goes on, because, when we discuss irreversibility, in the irreversible process, we went from A to B. So there is a sense of direction of time here, right? A was before, B was after. And therefore, we are saying that for an isolated, irreversible process, entropy can only increase with time. Well, it can either increase or stay the same.
So when did we consider that the path 1 was adiabatic before you wrote it down?
We considered here.
Oh, okay.
Yeah. Now, otherwise, we just have this thing, right? We just have this.
Yeah.
So when you wrote dq by t, integration of dq by t is less or equal to, is less or equal to 0. Does
Right.
this mean this sometimes get to the negative side? That means the entropy goes to negative.
No, here we know what is important is that the sum of the path here is reversible, and that is the reversible bit that we are playing with.
So
if
could
the
you
path
make
is
a comment on the irreversibility of the irreversibility of the adiabatic path?
Yeah, the entropy is never going to, it's going to increase. And you're saying, so I think
Yeah.
the entropy is usually not negative, but I think it's really the change of entropy which has the meaning. The way that entropy, that's a good question. Maybe there, usually entropy is not negative because when we go to statistical mechanics, which I'm hoping we'll do in a week or so, you will see the entropy actually it counts something. It's actually is something that is actually counting something. So it should not be negative.
Yeah.
so what does that mean on dq by t when it's less or equal to 0?
So it's not saying that dq by t is less than 0, less or equal to 0. It's saying that its integral over a closed path is less than or equal to 0.
So what does this mean graphically?
Mm, sorry, what do you mean graphically?
It means
Well, yeah, it means this
learning
thing.
from the graph.
Yeah, it means that if you have a closed path in state space, this integral is either 0 or negative in state space. Now, if it was completely all these paths were reversible, then this would be 0, and that's how we talked. We said that there exists a state function called entropy. So I'm probably not understanding the question you're asking. Can you try again?
So I'm asking, how does this integration work in this graph? I mean, which area divide minus which area
Oh, I see.
subtracted
Yeah,
by
no,
which
no, no.
area?
Yeah, I see. Right. I see what you're saying. Yeah, that's not on this graph. There is a different graph of S and T, and there, you can have like you're saying, if this integrate. So, for example, when we were doing energy, this was work, right? When we were doing the PV diagram. If this was, say, a Carnot cycle, it's not. But if it was a Carnot cycle, then that would be work, right? But here, this is no. We are not. There is no. We are not representing this thing graphically in this graph.
Oh, sorry, I understand.
Okay. Do you understand now?
Yes, sir.
Okay. Good. Okay. All right. So this is basically, for an adiabatic path. Now, if the path was both adiabatic and reversible, then in this equation, dq, this would also be 0, right? Mm. So if that is the case, then right. So if both path is both adiabatic, sorry, that's what I sorry. If path number 1 is both adiabatic and reversible, then
Then the integral should be 0, I guess.
yeah, and then S of B should be S of A. Right? Um, Now I'm having second thoughts about this. Let me see if I. Hmm. Okay, let me come back to this last comment, okay? I'm not 100% sure how to justify this right now. Okay. Do you guys have any idea?
This is implying that the irreversible process and the reversible process have the same entropy.
Yeah, exactly. Yeah. So
maybe the premise is false. Is that the problem? Like it can't be adiabatic and reversible?
it can be both adiabatic and reversible.
So maybe it's related to the not changing of internal energy or the isolation.
Right. So if it's okay, let me get back to that in the next class. Okay.
Okay, sir.
I don't have a very
Would this create a perpetual motion machine because both of the entropies are zero?
I mean, if you could like have, I don't think so. That's a good question. I don't think so. Now, like what you're saying is that if there is no friction, does that allow us to have a perpetual motion machine, right?
I suppose so, yeah.
Yeah. Is that correct? I mean, yeah. I mean, if there's a friction, of course, something goes. If you have a pendulum which there's no friction, it is going to forever be oscillating, right? So in that sense, it is a perpetual motion machine. Okay, so let me just get back to this part in the next lecture, but I think for us, this is actually quite a good enough and profound statement. And if you were to express this as a infinitesimal statement, you would say that the entropy, the change in entropy is always zero or greater than zero, okay? Here, delta means that the change, yeah. So I think, you know, there's a sense of time that is implied here. Okay, so in the next class, we will discuss in more detail what, you know, I'll try to come up with some examples of, you know, how to give a bit of flesh to this equation. And we'll try to, and we'll discuss some other thermodynamic concepts, okay? And so I hope you guys, I mean, this is a very subtle and difficult subject, so I am not expecting you to, I mean, I have a lot of questions about this, and I hope you guys too. And please send me some questions via Slack, and you know, hopefully I can think about this and before next class, and we can have a more interesting discussion going, okay? Any questions so far or comments? Maybe one of you figured out what I was trying to say about the equality.
I have a question.
Yeah.
Going back, I didn't want to ask this at the time because maybe the answer is going to be a little convoluted. But I've encountered this argument several times where the ratio of the functions that we used in the definition of temperature. Why are we allowed to arbitrarily set the temperature? Like at some point, I think we say that, okay, well, this is what we will call temperature.
Right. It doesn't have to be, yeah, we were like, we chose it to be a linear scale, right?
Yeah.
But we didn't have to choose it to be a linear scale. It just has to be in a way that, that identity of 1 minus eta has to be a ratio of the temperature function.
So am I right in thinking that we have a set of constraints, and any function that fulfills that constraint is worth calling temperature?
Yeah. And,
so we just go with the simplest one.
Yeah. And it's I mean, I can just basically take. It's just that what will happen is that if you don't take that, all the second law of thermodynamics and all, they will just look a lot more complicated unnecessarily.
Yeah, I see.
And but you can always do that, as long as the function is monotonic function of t. And okay, any other question?